Hi, and welcome to 3.4, the chain rule. Congratulations for making it this far. 3.4 will be considerably easier if you have successfully navigated your way through sections 3.1, 3.2, and 3.3 first. So once you feel like you're pretty comfortable with those sections, then I suggest moving on to section 3.4, the chain rule. So far we have rules, we have special rules when we have products of functions, we have special rules when we have quotients of functions. What the chain rule is going to do is help us when we're taking the derivative when we have the composition of functions. That is a function inside of a function. All right, well, what do I mean? Well, let's start simple. Let's suppose we just have the function y equals the sine of x. Straightforward, y equals sine x. We know the derivative is the cosine of x, right? Very simple. We learned that in 3.3. If we have y equals x cubed, then we know the derivative by the power rule. It's just 3x squared. Super easy. But what if I put this x cubed inside the sine? What's the derivative? What's the derivative of the sine of x cubed? We know the derivative of the outside function, which is the sine. We know the derivative of the inside function, which is x cubed. So can we use a combination of the cosine and 3x cubed to find the derivative? Yes, we can. But we have to be careful, just like the product and the quotient, we can't just take the derivative of the sine and the derivative of x cubed and smush them together. It will not produce the right result. So what we have is what we call the chain rule for the derivative. The chain rule written in notation looks a lot more horrible than the actual process. So this is the composition of functions. It's when we have one function inside of another function. So sometimes you see it written like this, f of g of x. We take the derivative. Right, so when we have the function inside of a function, what we do is we take the derivative of the outside function, leave the inside function alone, and then multiply by the derivative of what's inside. Right. So again, looks a lot horrible than the actual process. So what I tell my students to do is to identify the outside function and the inside function. So this is the outer, right, and this is the inner. So we have a function, so this is my in, right? This is in, this is out. So this is the derivative of the outside function, leaving the inside one alone, and then multiplied by the derivative of the inside function. So the derivative of the sine of x cubed is going to be, well, we take the derivative of the outside function, and the derivative of the outside function, the sine, is the cosine. We're going to leave what's inside alone, and then multiply by the derivative of what's inside. And the derivative of x cubed is 3x squared. Now again, we tend to rearrange this. I'm going to put the 3x squared out front times the cosine of x cubed, because it's super important to remember that this x cubed is inside the cosine, but this is 3x squared is multiplied by the entire cosine. We may not multiply these two pieces right here. We cannot call this 3x to the fifth. It would not be true. So to avoid that, we tend to put it out front. And the derivative of the sine of x cubed would be 3x squared times the cosine of x cubed. Now, if you're really super awesome with your algebra and your trig identities, you could do this using the limit definition of the derivative, but I'm promising you it's going to be horrible. So we want to get comfortable with using the chain rule and trust the rule. Again, the rules are proved in either the PowerPoint lecture notes, or you can look in your book for more detailed explanation of how the chain rule was derived. All right, so I said, let's find the derivative of 5x cubed plus x two different ways. All right, so notice f of x equals 5x cubed plus x squared really just means 5x cubed plus x times 5x cubed plus x, right? And then we're going to distribute this. 5x cubed and 5x cubed is 25x to the 6th. Let's hope I don't make an algebra mistake here. 5x cubed in x is 5x to the 4th. And then we have 5x to the 4th again, plus x squared. All right, so now we can just go take the derivative because now we have a polynomial. Right, actually, let's clean this up because we have 25x to the 6th, 5x to the 4th plus 5x to the 4th. We'll simplify that and call that 10x to the 4th plus x squared. So the derivative is going to be, well, we're going to bring the power out front. 25 times 6 is 150, right? X to the 5th plus 40x cubed plus 2x squared. Right, so that's one way to do it. Or we could use the chain rule. This is my inside function. So what we're doing to the inside function is we're squaring it. So for f of x equals 5x cubed plus x all squared, the derivative would be, well, we're squaring something, so we could use the power rule. We can bring the power out front and drop the power by 1. So that would be the derivative of the outside function. The derivative of something to a power, if the power is constant, we bring the power out front and drop the power by 1. So we'll bring the power out front, drop the power by 1, and we're going to leave what's inside. So it's going to be 5x cubed plus x. And then the chain rule says, now that you've taken the derivative of what's going on the outside, let's take the derivative of what's going on the inside. So the derivative of what's going on the inside, we ignore this, and the derivative of 5x cubed plus x is 15x squared plus 1. So that looks a little bit different than this, but if we do the work out, this is good. That's a power of 1, so we can ignore it or not worry about it. This is going to be 10x cubed plus 2x, right? All times 15x squared plus 1. And then we have two binomial expressions, so we're going to FOIL. Product of 10x cubed and 15x squared is 150x to the 5th, right? Here we have 10x cubes. And then here we have 30x cubes. The inners give me 30x cubes. And the outers give me, 2x, right? I see what I did right here. So I did. I hope you guys are on top of things. The derivative of x squared is just 2x. We don't need that one here. So careful, that does not go. Right, I was looking ahead and I knew I had to get 2x on the end. So again, tiny little algebra mistake, don't want to make those. Now we're just going to combine like terms. We get 150x to the 5th plus 40x cubed plus 2x. Right, same answer, two different ways. Right, so again, you might say, well, why would we bother using the chain rule? Well, what if I had this problem and instead of raising 5x cubed plus x and just to the power 2 squaring it, well, we could just simply FOIL it and use the power rule. What if I had to the 20th power? Do you really want to write 5x cubed plus x down 20 times and multiply that all out? My guess is your answer is no. So using the chain rule, so this is going to be my inside function, and I'm raising it to the 20th power, that's my outside function. So something to the 20th power, the derivative is going to be, well, anytime we have something to a constant power, we bring the power out front and we drop the power by 1. And we're going to leave the 5x cubed plus x inside. But then don't forget to multiply by the derivative of what's inside. So we have 20, 5x cubed plus x to the 19th power times the derivative of what's inside, 15x squared plus 1. And you do not need to distribute this all out. Leave it in this beautiful, nice factored form. That would be the end. A lot easier, zillions of times easier than multiplying that out 20 times. All right, so let's do a few more here. So again, these just take lots of practice. Let's find the derivative of the cosine of the sine of x. Now notice, I'm just going to write here, the cosine of the sine of x, the sine of theta, is not the same as the cosine of theta times the sine of theta. This is not a product. You may not use the product here. There is no theta here. The sine of x is inside the cosine function. So this is the outer function, is the cosine, and what's inside the cosine is the sine. Do not mistake compositions for products. If you can't separate them, like draw a line and have a complete function on each side of the line, then it is a composition. The cosine times the sine of theta does not make any sense. So this is not a product. So according to the chain rule, because we have a function inside of a function, the derivative is, you take the derivative of the outside function, the derivative of the cosine would be the negative sine, leave what's inside alone, then multiply by the derivative of what's inside. The derivative of the inside function would be the derivative of the sine of theta, which is the cosine of theta. So the derivative of the cosine of the sine of theta is the negative sine of the sine of theta. Now we have a product times the cosine of theta. Right, that would be the answer. All right, let's look at this guy. We have e to the power x to the fifth plus x. Now, if it was just e to the x, we know the derivative would just be e to the x. But we have this whole bunch of stuff. So this guy is my inner function. And the function out here, e, is the outer function. We stuck x to the fifth plus x inside the exponential function. So the derivative is going to be, well, the derivative of e is itself. So e, leave what's inside alone. And then we multiply by the derivative of the inside function, which is x to the fifth plus x. So the derivative would be 5, x to the fourth plus 1. Now here's where it's super important to make sure you include parentheses, especially if you're doing online homework, because if you don't include parentheses, you're only going to be multiplying this exponential term by the 5x to the fourth, but it's really being multiplied by both. So either you distribute or you include the parentheses. So the derivative of e to the power x to the fifth plus x is e to the x to the fifth plus x times the derivative of the power, which is 5x to the fourth plus 1. All right, let's do one more, and I'm going to give you a list of templates. All right, find the derivative of the secant of 2 to the x. We know the derivative of the secant is the secant tangent, right? So the derivative of the secant is that secant of x times the tangent of x. But the derivative of the secant of 2 to the x is much different because we have this inside function 2 to the x. So this is my inside function, and this is my outside function because 2 to the x is inside the secant. Now what's interesting is when we take the derivative of the secant and the cosecant, we start with 1x in the original function, but when we take the derivative, the variable appears twice. So you have to take that into consideration. So let's work with this guy. The derivative of the secant of something is going to be the secant. Now we don't just have x inside, we have 2 to the x. So it's going to be the secant of 2 to the x, tangent of 2 to the x. So whatever's inside this secant function is going to appear here and here. So that's the derivative of the outside function. The derivative of the secant is the secant tangent. Leave what's inside alone. We're going to replace the x's with 2 to the x's. Now take the derivative of 2 to the x, which is 2 to the x times the natural log of 2. And that's it. We can't do anything else with that. That would be the final answer. All right, so bear with me while I go through some templates. I think the next page will be super handy. The only way you get good at this and remember these is by doing lots of problems. So the power rule, x to the power. The derivative is the power, x to the power minus 1. But if we have something other than x to the power, then the derivative is, we bring the power out front, leave what's inside alone, drop the power by 1. So notice I just replaced x with what's inside of the power function, but then the difference is we multiply by the derivative of what's inside. Now, technically, we are doing that here because what we're raising to the power is x. So the derivative of what's inside, the derivative of x, we would be multiplying it just by 1. So we actually have been using the chain rule all along. We just didn't know it. All right, for the function y equals e to the x, the derivative is just e to the x. But if you have y is e to the something other than x, actually it does work for x also. The derivative is itself times the derivative of the power. So here's your template for the chain rule for e to the anything. The derivative of y equals a to the x for any positive base a is a to the x times the natural log of a. The derivative of a to the something would be a to the something times the natural log of the base. But then don't forget the chain rule, we tag on the derivative of that something. Oh, what did I do here? Oh, I gave you an extra one. That was a freebie. Sorry. Let's get rid of that guy. All right, the derivative of the sine of something. Well, the derivative of the sine is the cosine. And if it's just x, it's just the cosine of x. Now, technically, it would be times 1 with the chain rule, but we don't need to include that times 1. If it's the sine of something other than just x, the derivative is going to be the cosine of what's inside times the derivative of what's inside. Cosine. The derivative of the cosine, negative sine x. Remember, trig functions that start with c have negative derivatives. The derivative of the cosine of something, if it's other than x, it's the negative sine of that something times the derivative of what's inside. Sorry, that's just an extra one. Ignore that. All right, so we'll keep going. And yes, you want to remember these. You need to memorize these. The derivative of the tangent. Well, the derivative of the tangent we saw was the secant squared of x. So if we have something other than x inside the tangent, then the derivative is the secant squared of that something times the derivative of that something. The cosecant, well, I have a derivative that's a trig function that starts with c, so I know my derivative is going to be negative. Negative cosecant of x, cotangent of x. If I have something other than x inside the cosecant, the derivative is going to be negative cosecant of that something. Now this something is going to appear in both those spots. Cotangent of that something times the derivative of that something. The derivative of the secant is the secant of x, tangent of x. So this 1x appears twice. So now what's inside the secant, if it's something other than just x, it's going to be the secant of that something, tangent of that something, and then we're going to use the chain rule and multiply by the derivative of that something. Cotangent, starts with c, my derivative is going to be negative. The derivative of the cotangent is the negative cosecant squared of just x, unless we have something other than x inside the cotangent. Then the derivative is going to be negative cosecant squared of that something, so we just replace what's there and put it there, and then we multiply by the derivative of what's inside. All right, so let's try a couple more problems. Let's suppose I had the function y equals e to the power sine x to the fifth. Well, we know the derivative of e to the x is just e to the x, but if it's e to the something other than x, we're just going to write e to that something and then multiply by the derivative of that something. So I'm just going to box this because it's e to that power. So the derivative is going to be e to the sine of x to the fifth times the derivative of the sine of x to the fifth. We have to take the derivative. You can't just write this. This is a step to the end. Why I wrote this is you have to be really careful here, because now I'm looking to find the derivative of the sine of x to the fifth. I have a function inside of a function. I have to use the chain rule again. So the derivative, I'm going to ignore this piece for a minute. The derivative of the sine of x to the fifth, well, the derivative of the sine is the cosine. Leave what's inside alone, times the derivative of what's inside, 5x to the fourth. And then we're going to get this guy down for the ride. He's just going to be e to the sine x to the fifth. So the derivative of e to the sine of x to the fifth is e to the sine x to the fifth times the cosine of x to the fifth times 5x to the fourth. So we had to use the chain rule inside the chain rule. You can use the product rule inside the chain rule. You may have to use the quotient rule inside the chain rule. You may have to use the chain rule inside the quotient or product rules. Right, let's just wrap this up with finding the equation of a line. This isn't gone away. We are still going to find equations of lines tangent to curves. So we have to backpedal to what this means. Right, so to find the equation of a line tangent to this curve at this point, we need to know two things. We need to know the point, and we need to know the slope at this point. Well, the point, well, we just find f of pi over 6, right, which is the cosine fourth pi over 6, right? But now keep in mind, this means the cosine of pi over 6 all to the fourth power. And what's the cosine of pi over 6? Square root of 3 over 2, all to the fourth power, right? And the square root of 3 over 2, all to the fourth power. Well, square root of 3 times the square root of 3 times the square root of 3 times the square root of 3 is going to be 9. And 2 to the fourth, 2 times 2 is 4, times 2 is 8, times 16. So the point, actually I'm going to write it like this. The point is the point pi over 6, 9/16. Right, so to find the y coordinate of the point, I had to stick x into the function. Now I'm going to find the slope. I should have saved that. Slope. Well, the slope is just the derivative at pi over 6. That's going to be the slope. So let's find the derivative of the cosine to the 4th of x, which means the cosine of x to the 4th power. So it's often easier to write when we have trig functions to the powers. Remember that this is what this means. Now I'm going to use the chain rule because the derivative of something to the 4th power, this is a power function, except we don't have x inside. We have cosine of x inside, but I'll deal with that in a minute. So the derivative is we bring the power out front, leave what's inside alone, drop the power by 1 times the derivative of what's inside. All right, not super pretty, but we can handle it. I'm going to clean this up. This is -4 cosine of x cubed times the sine of x. I just like that better. So now let's find the derivative at pi over 6. Well, -4 cosine of pi over 6 cubed times the sine of pi over 6. Pi over 6 is 30 degrees. The sine of pi over 6 is 1/2. This is the square root of 3 over 2 cubed. And this is still -4. So it's -4 times the square root of 3 cubed over 2 times 1/2. Well, this 4 and these two 2's cancel out. So we were just at negative square root of 3 cubed, which is -3 square root of 3. So now we're just looking for the equation of the line. I'll write it down here. Let's see this, Ricky. All right, so we're finding the equation of the line. We know the point is the point pi over 6, 9/16. The slope is the derivative at pi over 6, which was -3 square root of 3. Now the equation of a line, I told you my favorite form to use is point slope form. Y minus the y value you know equals the slope times x minus the x value you know. So now let's clean this up. Y equals, that's going to be -3 square root of 3 times x. That times that becomes plus. That 3 and that 6 cancel out. So I get square root of 3 pi all over 2. Right, and then I'm going to add the 9/16. Not pretty, but calculus isn't easy. We should have some difficult answers. All right, kids, lots of practice. You get good at the chain rule by doing the chain rule. So have fun.